Okay, we're here at guide sheet number 6 on conservation laws. We're talking about momentum, and then we'll look a little bit at impulse and how momentum can be changed. All right, so first of all, what is momentum? Momentum depends on two quantities. It depends on the mass, the amount of stuff something is made of, and its velocity, not the speed. That's important. Velocity is a vector, and therefore momentum is going to be a vector. In symbol form, a lowercase p is, so lowercase p again is used for momentum. It goes back to the Latin word for impetus. You wouldn't want to use m because m is also mass, so that might get confusing. So they went with the lowercase p is equal to m times v. Now, one of the differences between momentum and energy is that momentum is a vector quantity, so direction is important. Again, momentum is a vector. Mass is a scalar multiplied by a vector. It turns out to be a vector. To completely describe momentum, you're therefore going to need not only a size, but also a direction. Units-wise, we're going to be talking about kilograms, which is mass, times meters per second, which would be velocity. So kilogram times meter per second in some kind of direction would work. Kilogram times meter per second squared, that's an acceleration. That's actually a force, so that doesn't work. This one doesn't have a direction, so that doesn't work. This is meters per second. That's a velocity. That doesn't work. 1.9 kilograms times meter per second to the west. That has both, so that works. This is kilograms per meter per second. That's a good unit, but it doesn't have a directions per se. So it's really not a complete description of momentum. So again, if you're trying to calculate momentum, you're going to need to know the mass of the moving object and the velocity of that object. Now, if the object is not moving, if it's at rest, its velocity will be 0, and therefore its momentum will be 0. I have two objects, object A, they're both moving at the same speed, 4 meters per second, but object A is twice as massive as object B. Therefore, compared to object B, object A has 2 times as much momentum. 4 times 4, 16 kilograms times meter per second. 2 times 4, 8 kilograms times meter per second. Okay, so A is twice as much. If they were different velocities, that wouldn't necessarily be true, but same velocity, twice as much mass. 16, calculate the momentum value. It's going to be the magnitude of a 2 kilogram brick moving through the air at 12 meters per second. That's going to be P equals mv is 2 kilograms times 12 meters per second is 24 kilogram times meter per second. 3.5 kilogram wagon moving along the sidewalk at 1.2 meters per second. That's going to be P equals mv equals 3.5 kilograms times 1.2 meters per second, which is going to be 4.2 kilograms times meters per second. 7, a little comparison. With what velocity must a 0.53 kilogram softball be moving to equal the momentum of a smaller mass 0.31 kilogram baseball moving at 21 meters per second? Now, since the softball has more mass, it's going to be moving slower, so it has to be less than 21 meters per second. If we want an equivalency, we'll just take the 0.53 kilograms times its velocity equals 0.31 kilograms times its velocity, and we'll solve for v. So 0.31 times 21, and we're going to divide that by 0.53, and we get 12.3. We only have two significant figures, so the new velocity of the softball is going to be 12 meters per second. Okay, so it has almost twice as much mass, so it's just about half as fast. A little more than half, because it's not quite half the mass, or twice as much mass. Okay, so we know what momentum is. It's a vector quantity. It's the product of the mass of an object multiplied by its velocity, the product multiplication. And direction, therefore, does matter because it's a vector and it is velocity. Now, how do we change the momentum of an object? And that's where this concept of impulse comes in. I take you back to the second law of motion. We said that all the forces, this is the law of acceleration, on an object are equal to its mass times its acceleration. Now, force is a vector quantity, acceleration is a vector quantity. By definition, the acceleration is also the change of the velocity, the rate of change of velocity. So change of velocity over change of time. That something occurs. So if I take this and put it in here, then the net force, and this means add up all the forces, whatever force is left over. So the net force acting on an object is equal to the mass of that object times its change of velocity divided by time. Now, what's done with this is to multiply through by time, and we end up with a new term. We have the net force on an object multiplied by time is equal to the mass times the change of velocity. This, mass times change of velocity, is the delta p, the change of momentum, and the F net times t is called the impulse. Okay. Symbol for impulse is actually J, capital J. I's and J's are pretty close to each other. They went with the J here because I is used for other things like current. Okay, so in a collision, an object experiences a force, back to the third law, acting for a certain amount of time, and that is known as an impulse, and that serves to change the momentum of an object. So the way we change the momentum of an object should make sense. It's how we get something to move or stop or slow down. We apply a force, some kind of unbalanced or net force. We apply that force over time. Force times time gives us an impulse, and that will determine how much the change of momentum is. Okay, so that's the first part of Guide Sheet 1. We'll look at the next part in our next episode.